Hello and welcome back. This is going to be our fourth lecture and we're going to be talking about sections 10.3 and 10.4, combinations, tree diagrams, tables, and sample spaces. Let's jump in. A selection of objects without regard to order is called a combination. And remember that the last time we were talking about permutation, which was a selection of objects where we did care about the order. So with combinations, order does not matter. Suppose you have 4 jacks from a standard deck of 52 cards. If you pick 2 of them, observe the difference in picking 2 cards when order matters and when it does not. So the 4 jacks are the Jack of Hearts, Jack of Diamonds, Jack of Spades, and the Jack of Clubs. All right, we want to pick 2. So let's discuss first when order matters. So we could have the Jack of Hearts, the Jack of Diamonds, the Jack of Hearts, the Jack of Spades, the Jack of Hearts, and the Jack of Clubs. Next, we'll do diamonds. So we could have the Jack of Diamonds, the Jack of Hearts, the Jack of Diamonds, the Jack of Spades, the Jack of Diamonds, and the Jack of Clubs. Next, we could have the Jack of Spades, the Jack of Hearts, the Jack of Spades, the Jack of Diamonds, the Jack of Spades, and the Jack of Clubs. And finally, we could have the Jack of Clubs, the Jack of Hearts, the Jack of Clubs, the Jack of Diamonds, the Jack of Clubs, and then the Jack of Spades. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's 12 possibilities, 12 outcomes. And that's when order matters. Because typically, when we are being dealt cards for a game, any kind, whether it be poker or otherwise, we generally do not care the order in which we are dealt the cards. So a hand containing, for example, a Jack of Hearts and a Jack of Diamonds would be considered the same hand as the Jack of Diamonds and the Jack of Hearts. However, if we're considering when the order in which we are dealt cards matters, these are not the same outcome. So these would be considered 2 different outcomes. So now we'll talk about when order does not matter. We would still start with the Jack of Hearts, the Jack of Diamonds, the Jack of Hearts, the Jack of Spades, and the Jack of Hearts, and the Jack of Clubs. However, when we moved on to diamonds, we already have a Jack of Diamonds and a Jack of Hearts. So now I only care about the Jack of Diamonds and the Jack of Spades, the Jack of Diamonds, the Jack of Clubs. Now we'll move on to the Jack of Spades. I already have spades with diamonds and I already have spades with hearts here. The only thing I'm missing is spades with clubs. So this is 1, 2, 3, 4, 5, 6 outcomes. So we can see how when we consider order and it matters, we get significantly more outcomes than when order does not matter. The formula for combinations is the number of combinations of n objects taking r at a time without replacement. It's denoted by a big C and is given by the formula here. So it's essentially the same thing as the permutations formula divided by r factorial, but it is written out nicely as n factorial divided by n minus r factorial times r factorial. And for an example, we're going to find the number of combinations of 10 objects taken 5 at a time. So we need our big C. We are choosing from 10 objects, and we are only taking 5 of them. So that makes our n 10 and our r 5. So that means we're going to have 10 factorial divided by 10 minus 5 factorial times 5 factorial. This is equal to 10 factorial divided by 5 factorial times 5 factorial. And if y'all remember from the last lecture, we can simplify factorials quite nicely. So I'll have 10, 9, 8, 7, 6 divided by 5, 4, 3, 2, 1. So you should get 252. Next example. While studying abroad one semester, Tom is required to visit 10 different cities. He plans to visit 3 of the 10 over a long visit. How many different ways can he choose the 3 to visit? Assume distance is not a factor. All right, so how do we know that this is a combinations problem? Well, he's not going to visit the same city 3 times, right? He's going to visit 3 different cities over the weekend. And we weren't told that the order matters, so we assume that it doesn't. So he doesn't care the order in which he visits the cities because distance is not a factor, the order doesn't matter. So this is a combinations problem because there's no repetition and we do not care about order. Again, no repetition. And order does not matter. So that's why it's a combinations problem. So we need our big C. We have 10 to choose from, and we are going to visit 3. And recall the formula, I'll write it over here. So we'll have our n is going to be 10 and our r is going to be 3. That's 10 factorial divided by 10 minus 3 factorial times 3 factorial. This is equal to 10 factorial divided by 7 factorial 3 factorial, which is equal to 10 times 9 times 8 divided by 3 times 2 times 1, since we're going to knock out numbers 7 and below from the 10 factorial. All right. This is equal to 120. So there are 100 different. Next example. At one high school, the student government consists of 7 seniors and 5 juniors. How many different committees can be chosen with 3 seniors and 2 juniors? So now this is kind of a compound combination problem. We weren't told that order matters, so we know order doesn't matter. And we're also going to assume that no person can hold all 3 positions. So 1 senior cannot be 3 seniors, which means that we have no repetition. So it's a combinations problem, and we will be using the combinations formula. So I'll write the formula for y'all. All right, and then first we'll do seniors. Of the seniors, there are 7 total that we're picking from, and we want to choose 3. We're going to multiply this by that counting principle we learned last time. You could think of this as K1 and K2. Of our juniors, there are 5 juniors and we are choosing 2 of them. So this is going to be 7 factorial divided by 7 minus 3 factorial times 3 factorial, multiplied by 5 factorial divided by 5 minus 2 factorial times 2 factorial. This is going to be equal to 7 factorial divided by 4 factorial times 3 factorial, multiplied by 5 factorial divided by 3 factorial times 2 factorial. We can further simplify each of these individually before we start to multiply them together. So 7 times 6 times 5 divided by 3 times 2 times 1, if we want to cancel out this 4 factorial. And then we'll multiply that by 5 times 4 divided by 2 times 1 by knocking out this 3 factorial. You should get 175. Moving on. A tree diagram is a diagram consisting of branches corresponding to the outcomes or 2 or more probability experiments that are done in sequence. Example, construct a tree diagram to find the sample space for flipping a coin 3 times. All right, so on the first flip, so we'll call this flip 1, we have 2 options. We can get heads or tails. All right. On flip 2, we could also get heads or tails, but it will depend on what we've gotten first. So we could have gotten heads on flip 1, heads on flip 2, or heads on flip 1, tails on flip 2. Similarly, with tails. Next is going to be flip 3. So we could have gotten heads or tails, and again, heads or tails. So this is a tree diagram showing all of the possible outcomes. So just to pick on one, we could have flipped tails, then heads, then tails. That would be a possible outcome. A coin is flipped and then a die is rolled. Use the tree diagram to find the probability of getting heads on the coin and then an even number on the die. So we can see here from this table that you can get heads or tails from the coin flip, and then you can get numbers 1 through 6 on the die. So if we definitely want heads, we're looking up here. And then we also want an even number. So that's going to be 2, 4, or 6. So looking at our sample space over here, which is our list of outcomes, our sample space would be heads and then a 1, heads and then a 2, and then etc. So we can see that we have 12 total outcomes. How many events give us first heads and then an even number? It's going to be 1, 2, 3. So that means the probability of getting heads, then an even number is equal to 3 out of 12, which simplifies to a fourth. Moving on. Another way of determining a sample space is by making a table. So in the previous example, this was a tree diagram. This is a table. Consider the sample space of selecting a card from the standard deck of 52 cards. So we can use this table to also find probability. So we know that there are 52 cards and thus 52 outcomes. So if you wanted to know, for example, the probability of drawing an ace, you can look up here at the table and see that you have 1, 2, 3, 4 aces. So that would be 4 out of 52, which simplifies to 1 out of 13. Similarly, if you wanted to find the probability of drawing, say, a spade, you could count all of the spade cards as well. So if you count all of these cards, you would get 13 total spade cards. So that would mean we would have 13 out of 52, which simplifies to a fourth. Next example is consider rolling 2 six-sided die and construct the sample space of all possible outcomes by making a table. So I'm going to show y'all how to make this table. So I'll have 1, 2, 3, 4, 5, 6. Similarly, 1, 2, 3, 4, 5, 6 up here as well. Because when I roll the first die, I have options 1 through 6, and then when I roll the second die, I also have options 1 through 6. So then we can start pairing these together. So I can get a 1 and a 1, a 1 and a 2, a 1 and a 3, a 1 and a 4, a 1 and a 5, a 1 and a 6. And I'm going to do this going all the way down this whole table. All right, now I finished that. So this is the sample space of all possible outcomes. Now, if we sit here and count them, we would count that there are 36. But we could also note that since they're both six-sided die, 6 times 6 is 36. So there are 36 outcomes. An interesting thought, if you were to roll 2 8-sided die instead of 6-sided die, you would have 64 outcomes because 8 times 8 is 64. So the more sides on the die, the higher number of outcomes you would have. Let's answer some following questions. So we want to figure out the probability of getting any of the following. First is going to be a sum of 8. So if we scroll back up, we want to look at all of the possible options where we will get a sum of 8 when we add the two numbers together from rolling the die. So I'm actually going to start in the 6 column. So 6 plus 2 is equal to 8. So here I have a 2 and a 6. Next I'll go down to 5. 5 plus 3 is 8. So here I have a 3 and a 5. And then we'll go to 4. 4 and 4 is 8. Moving down to 3, 3 and 5 is 8. And then down to 2, we have 6 and 2. So that is 1, 2, 3, 4, 5. So 5 out of 36. You could also write this probability as 0.139. Next, let's figure out the probability of getting doubles, or the same number on each side. Looking back up here at our table, we can see that the doubles go along this diagonal here. There are no other doubles across the rest of the table. So we have 1, 2, 3, 4, 5, 6 doubles. So that gives us 6 out of 36. which you could also write as 1/6 or approximately 0.167. Lastly, we want to figure out the probability of getting a sum less than 5. So I want to figure out what two numbers add together to get a number specifically less than 5 and not equal to 5. So I'm going to start with 1. 1 plus 1 is 2, so this one will work. 2 plus 1 is 3, so this one will work, which means 1 plus 2 will also work. 3 plus 1 is 4, so this one will work, which means 1 plus 3 will also work. However, 4 plus 1 is 5, and we want specifically a sum less than 5, so I don't want that number. Next, we'll move on to 2's. 2 and 2 is 4, so I want that one. However, 2 and 3 is 5, and 3 and 2 is 5, so I don't want either of those. That leaves only this top corner up here, my events that I am interested in. 1, 2, 3, 4, 5, 6. 6 events. So again, that's 6 out of 36, which simplifies to 1/6 or approximately 0.167. This concludes our lecture for today. Thank you so much for tuning in for our 4th lecture. I hope you have a lovely rest of the day.